Okay. Done it. If people online have questions along the way, I'm not watching chat, so just unmute and scream at me if I notice. Okay. Let's get started. So how AI works, depending on who you ask, the answer might be it doesn't, but we'll see. So understanding LLMs under the hood, how to control them, how to integrate them into your code. And yes, I am recording here. All right, let's get started.
I'll watch the chat.
You'll watch? Okay, thank you. You're also welcome to scream anybody or type to Grant. Okay. So what is an AI model? Hard to define. I'll define it as it's a thing that takes some input, does some calculations with it, and returns some output. So let's take a hypothetical example. Let's say we're Zillow, and we want to be able to make predictions on housing prices based on the size of the house. So pretend I'm not getting distracted. Come on. Might need a chair.
You don't sit in.
We're still filtering in here.
The laptops are for the multitasking.
You're going to start locking the door for this after.
Yep. Make sure no one else gets in.
Yeah.
Thanks.
More chairs.
Okay, let's see. So where are we at? So we're Zillow. We want to make predictions. We use AI to make predictions on how much a new house is going to sell for based on how big it is. So our output there is the sale price. Our input is the size of the house. And we want to be able to do some calculations along the way. So what might that look like? It might look like a very familiar math formula you saw in school. Y equals mx plus b. Very simple linear equation here, where our y is our sale price, our m is our price per square foot, our x is the square feet of the house, and b is, let's say, a fixed cost of the plot of land that house is on. So in order to do our calculations, to go from our input, the square feet, to our output, the sale price, we need to know those values for the price per square foot and the cost of the plots. We need to be able to find our m and our b. And those values, these other things that aren't our inputs and our outputs, these are called the parameters of our model. So the takeaway here is that there's no magic, it's just math. The AI models use these parameters to help map from inputs to outputs by describing the relationships between that input and that output. So how do we find these parameters? I think Mitch or Kyan, you can help me out here. So the process of finding these parameters, the values for these parameters, is called training our model. I'll let you know in a second here. So what we can do is we can use some examples. Let's say we've recorded some previous examples of houses that have sold. We've written down the price and the size of it, and we've drawn a nice little graph. And we want to adjust the values of our parameters until it fits. So go ahead and play with those sliders there and see if we can figure out the right value here. You might have to click and drag.
I want a really big house. So 417 square feet.
Great. You want to get the other one right too? So we're trying to fit that line through our examples here.
Oh, we're trying to fit it through? Oops. All right. That's not going to work out. I can't have a big house. Dream's ruined. Okay. And then I think probably as good as I'm going to get it.
Awesome. Works fine for me. Thank you. I'll call you back in a second here. I'll go too far. Okay, so we've done it. We've trained our model. So by using examples here, we can iteratively play around and try and figure out what good values would be for our parameters for our model. And now that we've done this, we could start making predictions of this. We could put in some input square feet and figure out what our output price would be for our house. So takeaway there, based on examples, we can figure out what good values would be. And this is why data is important in training models. These examples are very helpful for being able to figure out what these parameters values might look like. Any questions so far? Awesome. Moving right along. So on complexity here, the more of these parameters that we have, the more complex the relationships are that we can capture. Go ahead, please. So now we've moved up from having 2 parameters here to instead of having 4 parameters. And we'll see what we can figure out here.
Okay. That's nope.
Don't feel bad, Ken. Clayton made me do this at home. It took me like 10 minutes to do these.
Okay, so which one adjusts this one?
You don't have to get it perfect.
Great. You know you're fine.
I think
You're gonna be here a long time.
Okay.
Brute force, brute force.
Yeah.
I think
Ooh,
if you don't get it perfect, it will be a better example of the AI.
that's okay. Well,
That's
thank you for trying. I think you've done a wonderful job. That's better than I could have done. Okay, so that's our 4-parameter example. And the takeaway there is just that the more of these parameters we have, the more complex the relationships are, the more squiggly the line is that we can draw along the way. And modern LLMs, it depends on which one you use, but a lot of them have about 400 billion of these parameters. So the takeaway there is that these modern LLMs can handle extremely complex patterns, but are also very computationally expensive, both in like at inference time, if I wanted to make a prediction for a price here, it would be a lot of calculations, but especially at training time. Pan did a wonderful job with these 4, but if we give them 400 billion, it might take more than a couple minutes there along the way.
Yeah.
So that might take more time than we have in our meeting. So the question is, do we have to do these by hand? Do we have to find this by hand? And the answer is no. Luckily, computers are very fast at iteratively updating the parameters for us. And we'll see how well this does. I didn't make this very smart, so we'll see. I'd say that did okay enough. So I've pressed a button here. It's done some trial and error for me. We've brute forced our way to having a good enough fit through our line to start with. It would have been nice if it captured that one at the edge here, but it's done an okay job. So takeaway there is that computers are very fast at solving for these parameters. And the idea of letting computers find these values for us is pretty central to the field of machine learning. That instead of training our model by hand by adjusting those knobs and dials, computers can very quickly do that math for us.
Can I ask a question?
Please.
So I don't think a computer is brute forcing it, going through literally every single parameter, tweaking it through all its options. So what kind of algorithms go into like finding the best guess?
Ooh, finding the best guess. So you could do it just by brute forcing. You're right, this isn't doing it. This is actually leveraging some calculus, but let's come back to that question in a second here.
Okay.
Let's move on to the next slide. So let's see what this might look like under the hood. And most of us are C# people, and by us I mean not me, but hopefully this helps along the way. So let's see a little simple C# example. So we need to be able to record our housing prices. So let's be able to record square feet and the price of the house. That's our input and our output. And we'll make a linear model class, and it has a couple of parameters. So that price per square foot, our M, and our cost of a plot of land, our B. We don't know what those are yet. We need to be able to find them. So let's start off by setting them to 0. And our model also needs to be able to make predictions. So let's give it a little predict method here that takes in our input of the square feet and then multiplies that by our parameter and has the other parameter and spits out some prediction for our price. And we need to be able to train our model. So let's figure out a nice training loop. It should take in an array of these examples we've recorded down. And for each of these examples, let's do something simple. Let's make a prediction to start with, just with the parameters it has, and compare that against the actual price we saw for that specific example. And if our predicted price is too low, if it's below the actual thing, let's just nudge the price per square foot up a little bit and the cost of land. So we'll move our parameters up a little bit if we're guessing too low. And if we're guessing too high, then we'll move our parameters down a little bit. And then we'll just return the model that we have with our updated parameters. And so our program running this, hopefully we've defined more than 2 examples here, but we have our array of examples of these house prices, and we can make our model, and we can pass in our examples to train it, and then it'll return a trained model for us. So this isn't a very smart loop here. There's definitely room for improvement. To touch on some potential algorithms, there's some cool stuff you can do with linear algebra to do this in just 1 step. It involves inverting and transposing matrices. There's also some cool stuff you can do in calculus involving partial derivatives to calculate something called a gradient to figure out which direction you should move in along the way. So there's definitely ways we can make this more efficient, but those are optimizations. This in and of itself could work for simple examples. And instead of updating by a fixed amount, maybe we'll start by doing big updates, and then as we get closer to the right answer, we'll narrow in a little bit. So maybe we have more of a learning schedule built into. But fundamentally, this is the idea of training a model with examples, updating parameters, and then at the end being able to make predictions with it. And that's it. That's our however many lines of C# that is. We've done the AIs. Any questions so far? Wait for you to finish chewing there.
So you use the term machine learning,
Uh-huh.
and AI.
Yep.
You using them interchangeably, or do you mean different things?
Ooh, I mean different things. AI is overloaded at this point. I used to think of it as like a big bubble, and machine learning is a part of that. I think when I think of machine learning, I think of this training loop in here where we've passed in some examples, and based on those examples, computer is tweaking our parameters for us. AI maybe is the thing that gets spit out at the other end. This is an AI model, or AI is the entire discipline of machine learning plus any other more less machine learned approaches to
So
getting
you don't
those parameters. So I don't know what it means. No one knows what it means. Or maybe they
I think
do.
There's some
We
marketing
disagree.
under the AI.
Yeah. When you see AI models, they're basically little math formulas with some software around them. And machine learning to me is computers figuring out what calculations those AI models do rather than explicitly programming in if this, then that. Simplistic opinion of it. Does that almost answer your question?
Yeah, I think it's close.
Visible enough.
So,
Go ahead.
so maybe LLM is a better name than AI model, or is that kind of?
LLM would certainly be more specific. So let's
It's not an LLM.
this is not an LLM. No, this is just an AI model. And let's move towards an LLM. That's a great question. So far we've just been multiplying numbers together. We've just been doing math. But how do we do math with words? So if you want to make a model that make predictions with language instead, and models just do math, positive, just do math. How do we do math with these words? Well, we could take all the words we know and map each word to a random number. And then we could do math with those numbers. So maybe apple is 1, banana is 2, uranium is 9, just some arbitrary mapping to start with, but it doesn't quite feel right. What do these numbers mean? But this random assignment doesn't feel like it helps us represent the relationships between these words very well. That it feels like similar words, it'd be nicer if they had more similar numbers. So let's read all of the internet and see which words are used together frequently, maybe see how they're used, and try and more cleverly arrange our mapping here so that similar words have more similar numbers. So maybe apple and banana are still close together, but we've moved titanium and uranium to be a little close together. So this feels a little better. Maybe it's not quite obvious yet how we then make predictions with these, but we're just figuring out how we can represent words with numbers so we can do math with those numbers somehow. But these integers, they still have a bit of a problem. There's not much nuance to them. They don't capture that idea of relative similarity, that there should be a smaller distance between apple and banana than between leaf and dog, for example, between monkey and titanium, that the idea that these words aren't all equidistant from each other. And we want to be able to capture the closer the proximities between these two things. So instead of using integers, maybe we can use decimals along the way too. So apple and banana can now be very, very close together. And then there's a bit of a jump to get from a tree. Moving down here, titanium and uranium are very close together. There's a big jump from monkey, for example. So these decimals, they feel a little better than using an integer, but there's still a problem with this. Well, any questions before I go on? I'm sure there's lots of questions, but any questions I should answer? Okay, keep going. So it's a problem though that there's different types of similar, right? That if we only have one number, we can't capture all those different types of similarities. That monkeys and dogs are both animals, they should be close, but I know that monkey should also be close to banana somehow. So instead of using a single decimal number to represent a word, let's use multiple numbers. And for now, let's say that each dimension captures a different type of similarity. That maybe our first column is like the edibleness of it, and the livingness, and the metalness, and the tropicalness. And by having multiple of these numbers, we can capture different relationships. That now our monkey and our banana can both be high in tropicalness, but we can have a difference between them in quite how alive they are and how edible that they are. And AI models, when they're using these arrays of numbers to represent a concept, it doesn't always perfectly map to a column, a perfect column as we would see it. So it's not always entirely true that one of these columns represents the edibleness. That edibleness idea might be spread across multiple, but to think about it, I find it helpful just to think that this number is this concept. It makes it easier to picture in my head. And the idea here is that we've discovered the idea of embeddings, that we can use arrays of numbers that describe words, where similar words have similar numbers, but with different layers of similarity along the way. Does that make any sense? This is a lot closer, yeah. That there's an idea of being able to represent our words with big long numbers. So instead of having 4 A lot of them, they'll maybe have 1,000 of these dimensions, and those dimensions, those 1,000 dimensions don't perfectly map onto edibleness. Maybe edibleness is the combination of a few things. That's something that the machine learns to do by having a bunch of calculations happen. But this is a pretty close approximate idea of it.
Specifically, the machine is kind of in charge of generating these embeddings, like somebody doesn't go through and.
Right. Cayenne, unfortunately, is not by hand mapping out exactly what these should be. Yeah, better things to do. Well, maybe yes.
And these are pretty orthogonal, like metalness and tropicalness
Yes.
are unrelated. And you talked about them being, some of these being spread across multiple dimensions.
Mhm.
So that's interesting.
Yeah. Yeah. In reality, the concept of the tropicalness of something may not be like, this idea of orthogonality. I think I have my webcam on. That the tropicalness might actually be like between some things. It's the combination of multiple of these.
Edibleness and livingness, those
Yeah.
are not necessarily orthogonal.
Right. Those might be a little closer together too. It's so. So there's kind of a multiplicative nature that there aren't just 1,000 things that it can keep track of by having 1,000 dimensions, that like the space between these dimensions starts to have meaning, and the combinations of them, I guess permutations would be a better term there. Yeah.
So like this, could these be considered like dimensions in a vector?
Exactly.
That's
Yeah.
exactly what
This would be
it is, yeah.
4 dimensions in a vector. And
So,
this would do 1 vector.
I could perform like vector operations, like to see if I want something to be completely different or complete opposite, like I could do vector operations on it, or if I want to find something like similar.
Yeah, definitely. And there's different types of vector operations you might do. One of them might be something called the cosine similarity, where if you think of, let's do it in 2 dimensions. Let's just look at a couple of these, like livingness and metalness. If you were to plot that out, you could plot each of these words as being like a line pointing out in a direction. And you could look at these lines and see the angle between them. And so things that are more similar might have a smaller angle, and things that are more different might have a bigger angle being away from each other. But you could also do other things like dot products. Those are very relevant. Probably cross product. Any other matrix multiplication may or may not have meaning. Dot products especially, those are pretty big. This idea of like projecting.
The most common example of this is like royalness and then gender. So it's 2 dimensions where it's male, female, and then it is royal and peasant. So like a queen and a king are both royal, but on different ends of the gender spectrum. So then, but a peasant is like a male typically, right? Stereotypically, you think of a peasant as a male that is low on royalness. So the exact opposite of a peasant would be a queen, and the exact opposite of like waitress or whatever would be a king, right? Because they're orthogonal in both dimensions. So that's where you're getting to the vector operation. That's kind of the stereotypical example.
Do you know why they talk about them as vectors and not points? Because they're kind of the same,
Yeah.
but there is like, why they choose to like show them as a line as opposed to.
Well, I think it's important to think about the thing that he was saying earlier, that typically topicality is contained within multiple columns, because we don't know that like column A is edibleness, right? So if you're thinking about a vector, you only really ever think of embedding as multiple dimensions, because then it only becomes valid in multiple dimensions. So I think having it in the realm that it's already going to be used in, like computationally.
Yeah, not talking about different dimensions. It's a representational issue, right?
Yeah. And
Represent them as this thing going out from 0. I guess the end of the arrow is the point.
yeah, the end of the arrow is the point. So you could totally do either one. Where I think it's helpful to think about them as arrows instead of points is, let's see, I don't think I have a good example here, but imagine you have like 2 overlapping arrows, nearly overlapping, but one of them's not quite as far. That's like a little bit edibleness and a little bit livingness versus a lot of edibleness and a lot of livingness. Like those 2 lines are still close to each other, so those 2 concepts might still be, whatever word is being represented by those arrows might still be close to each other. But it's like the relativeness of a thing is more important than the absolute difference. That this point, if you're viewing it just as a point and looking at like Euclidean distances, the things around it may not be as conceptually similar as things that just happen to lie on similar lines. That let's see, direction and magnitude, that the direction is more important than the magnitude in some cases, and things that overlap directionally, conceptually, map to be more similar than things that have similar magnitudes. Sometimes.
So
But you can use both.
I have one of the final ones. So since these are mostly like they could be represented as vectors. Is most of the computation done by linear algebra?
Yes.
Okay. No brute force.
Well, you could. It'd take a minute though.
Yeah.
Okay. Great questions. This is fun. Let's keep going though. So we're finding numbers for words. Which of these words do we find the numbers for? So it'd be hard to do it for all words because there's a lot of different words and a lot of variations for them. And it'd be nice if our language model could account for things like typos and things like variable names. So my cool variable name. It's cool if somehow we could represent that and also be able to pick on the type of like intelligible versus intelligible. Like somehow it'd be nice if we could represent these as well. So we could use just letters. So instead, on the previous slide, instead of mapping whole words to these embeddings, we could just map letters to it, but it's really hard to capture the meanings. Like, what is S similar to? Other consonants, maybe. It's really hard to really capture meaning when we go too small, and it's hard to figure out all of them when we go too big. So instead of finding these embeddings for every possible word, instead maybe let's use a middle ground where we find numbers for a lot of these common words and also for common parts of other words. We'll give that a name. We'll call this the process of tokenization, of breaking text into smaller pieces called tokens. So as a conceptual example, let's say we have a sentence. We could pick some common words along with some pieces of larger words like photosynthesis, and we want to break this down into tokens where each of these tokens are things that will have numbers mapped to. So for a lot of these common words, maybe there's a one-to-one relationship between a word and a token. But for something like photosynthesis, maybe that gets broken into photo and synthesis as two separate tokens that we have these most of the time, hopefully, these building blocks that very closely map to actual words, but also we could build more complex words out of it. My cool variable name, maybe that's something though. Now, again, along with the idea of embeddings, that because Cayenne isn't by hand figuring out what all these mappings should be, computers are trying to find these patterns for us. They don't always perfectly map to things the way that we might think they would. So in my hypothetical example here, photosynthesis are my two tokens. And I find that's a very helpful way of thinking about how they're built up over time. And it'll vary by model and how they actually work. But if we look at GPT-4o, this tokenizer, it actually gets broken into photos and synthesis, which is a little less meaningful to me, but it doesn't need to mean something to me as long as the model can figure out enough meaning behind synthesis and how it's used to be able to put it together afterwards. But conceptually, I really like to think about this as words and the building blocks of bigger words. And this is why tokens exist, because they're the middle ground between I have to know every word and I can only use very small letters and I have to very complexly build up meanings for those letters. Make sense?
There's a question online on the last slide where was it important that there weren't any zeros?
No, these could be any numbers you want them to be. I think normally they'll be between like -1 and 1. Just to make it easy for me, I didn't want to have to figure out what negative livingness was, but it's a great question. Usually there's some negative component to it too and a positive component.
Zombie.
Yeah, that would be a great example. When you do a lunch and learn, you should have zombie in this slide. Okay. Any other questions on these two slides? Okay, so this is the why tokens, because we need that middle ground. All right, and these tokens are all that our model is going to learn how to represent and understand. But quick warning on these. So this tokenization is actually kind of a limitation. So it's part of why language models are really bad at math and counting letters within words. And I'll come back to what that means in a second here. But if you ask it a question like, oh, what is 70,893 times 309,597. So what's that?
You need commas.
I do need commas, but I didn't want to add commas because then I'd have to figure out where commas go up here. When we ask AI to do this problem, we put this into ChatGPT and it breaks it down into tokens. It doesn't see this as 70,893. It sees this as, let's say the word, the token 708, followed by a 93, followed by a times, followed by, instead of 309,597, 309, and then 597. That it doesn't see this number as one thing, it breaks it down into pieces that don't always perfectly make sense for why it's broken it down into those pieces. And it somewhat limits its ability to then do math with those, that it's treating these the same as it would words. And it's doing math on the representations behind these tokens, not on these numbers themselves. And so when you ask it to do math, the calculator gets a slightly different answer. And it's amazing to me that ChatGPT can actually get close on this one. But you see, it's like, I got some of it. Yeah, it's pretty good. It's good enough for a lot of things. But yeah, asking it to do math is a fundamental limitation there when you're asking it to just do those token operations. And it's also bad at like letter counting. So when you ask how many times does the letter R appear in strawberry, it uses this as straw and berry. It can't break it down into smaller pieces than that. So unless someone on the internet has already written out that there are 4R or three R's in strawberry, whatever that number is, it doesn't really have a good way of introspecting inside of a token to be able to get to it. So the tokenized representation introduces some limitations into what the model can see, and sometimes it's important. Okay, so where are we at? Bottom of the page. So far, we can take text, we can break it into tokens, and we can represent those tokens somehow with our arrays of numbers, our vectors, our embeddings, whatever word you want to use to describe that. But how do we make new tokens? How do we generate the next token? So let's think through a process of what that might look like. To generate that next token, AI needs to look at all those previous words, the previous tokens, understand what they mean together, and then figure out what should come next. So let's look at an example. Imagine we've asked Copilot to finish our sentence below. That monkey ate my. It has to complete the next token for us. So let's break it down into our tokens. That monkey ate my. Lucky for us, it very nicely mapped. We didn't have to break anything into mung and key. And we've given, we found the numbers that are associated with those tokens as well. So we have our numerical representations of this sentence so far after breaking it down into tokens. So we just have these arrays of numbers that represent the sentence. And now we need to figure out which token comes next. And this is a bit of an abridged version. If you remember on an earlier note, there's something like 400 billion parameters in these models and take up a lot of drawing room. But let's look at some of the pieces that might happen along the way. So one thing I might do, looking at this context, I might look at all the previous words and ask, which of these words are the most important for predicting what comes next? So it might calculate how much attention it needs to pay to each of these words. So in this case, it's done some calculations, it's done some multiplications against both these embeddings that it knows, and there's probably some other parameters that it's learned along the way in order to do this. This is like our price per square foot, other parameters it's learned. And it's done some multiplications and it's figured out that monkey and 8 appear to be the most important tokens in this sentence. Not that that and my aren't important, but it's tried to figure out, all right, in all these tokens, which ones should I pay the most attention to? And it's given some attention score to those. Then,
how does that part work?
Many matrix operations.
You're basically finding the one that has the highest amount of diagonality, but like basically the strongest direction, right? In a plane.
Not necessarily. So let's see. I'm not going to be capable of explaining this eloquently and in a way that'll actually make sense. But in all these, to try and take a stab at it anyway, though, all these tokens, they don't actually have just one array of numbers. They actually get 3, where each array, each vector represents a different thing. They have a query, a key, and a value, and their associated queries get multiplied against the keys of all the other tokens, and it uses that dot product between them to figure out what the intention should be. Part of it. There's more, but that's a lot of it. There's a lot of multiplications that happen, and the end result is that somehow there's an attention score associated with it. I don't know that it matters as much what that calculation is, but rather that there's some part of these calculations that it does where it tries to figure out which tokens are more important than others. That's later on. Next, very hand wavy. The hands will wave a lot. Okay, next thing. So we figured out our attention scores. Let's calculate some kind of a weighted average of all of our word vectors we've inputted so far. So some of these are more important than others, and we'll represent that by calculating some kind of a weighted average, and maybe we'll multiply our vectors together afterwards. It'll keep getting more hand wavy, unfortunately. But there's important bits at the beginning and at the end. The middle, the goo in the middle is very. But so we've calculated something that somehow represents the context so far, where there's a lot of monkey in here, there's a lot of 8 in here. Those are the more important things, and maybe some I. And this isn't the final answer yet. So this is a summary of what's happened so far. Next, our AI model has to run through a few more calculations to think about, okay, so these are the numbers that represent what's happened so far. Somehow I need to calculate that next word, that next token. And so it does more math. Let's not worry about what that math is, but somehow it does more math along the way. And we calculate some vector that represents, okay, here's an input vector that represents what's happened so far. Here's an output vector that would feel like a good fit for what might come next. And we take that output vector, that prediction vector, and we'll compare it against the vectors for every token that our model knows. So if we've given our model a vocabulary of like, I don't know, 20,000 or so tokens, we'll calculate a score for each of our tokens to see how close it is to our prediction vector here. So let's see a little visual here. That we have our prediction, it's our green, and then it looks like the closest other token is a banana. So banana is our closest one. Maybe apple's next, and then can't quite tell. It's getting a little busy here, to be honest. But somehow we figured out which ones are the closest, and the closer that they are, let's give them a higher score. So I'll look up here that banana looks like it was the closest. Just looking at it, closest. So it'll get a higher score. Apple, not quite as good, a lower score. Face, luckily, is low down, and then phone is very, very low, so not very similar at all. And this for all the other tokens that our model has learned about so far. And so we have our final scores for each possible next token. And our actual big 400 billion parameter AI model might do this multiple times with different perspectives. Maybe it'll pay more attention to some tokens for one part of the calculation, pay more attention to some tokens for another calculation, and then somehow multiply all those together to figure out what our next token scores should be. And so if you take away nothing else from this slide, it's our input text is broken into tokens. Somehow there's something that represents the meaning of those tokens with numbers. It does some kind of calculations. And at this step, it's given scores to all of the possible next tokens that it cares about. And if you take nothing else from this slide, you should have input, output here with these scores. So we have our scores. Right? Banana has a high score. Apple has a lower score. There's a question of which one do we pick? Which one of these scores do we pick? So we could just take the highest score. We could just take banana, but that starts to feel a bit too robotic, because that would mean that every time we ask our AI model, how are you? It would give the exact same response every time, and that doesn't really feel like AI. So
We don't do that every day.
that's true. Maybe it would be more human to just if and good. But in general, we want it to be maybe a little bit different each time. We don't want to just pick totally randomly. So instead, let's convert our scores to probabilities and then sample from that probability distribution where we have some balance between correctness and creativity, where most of the time it'll pick banana, but sometimes it'll pick apple, and more rarely it'll pick face, unfortunately, and then phone down here. So we'll probably pick banana, but we might not. And this is very important, that this idea of randomness is intentionally baked into the model's predictions, that the right token might get a higher score, but there's a necessary and intentional chance that it can pick the wrong token. This idea of scores to probabilities is very important.
And this is a relatively concrete example. I think many of the things, it's not so concrete. Where it could go, like if you're in the middle of a sentence and you could have said therefore or because. And
Definitely.
those may be very, very close, and it might have to type in one accent.
Yeah, and that's a virtue of the model, that it can be creative and do different things. But this is like, it's good and it's also bad. It's kind of this necessary evil. But it's a question of, okay, we're adding these probabilities. We're adding this non-determinism to the model. So can we have some level of control over it? The answer is yes. So how do we control the model? So unlike that hand-wavy calculation goo in the middle, these scores are very easy to interpret and very much more possible to control how we go about translating these into probabilities. So there's a couple of things we might control, like the temperature in the top P. So temperature controls how we map from a score to a probability. Right now, our high scoring banana has a very high probability of being chosen, but we can adjust this temperature parameter to instead make it less likely to just be banana, that we can make it more creative by changing how we map between that high score and our probabilities afterwards. So now there's a much higher chance we'll pick apple. And it can go the other way too, that maybe we can turn down the temperature and make it much more likely we'll be that more robotic response of just picking banana every time. But it doesn't quite go to 0 there. So that's temperature. And there's another knob and lever we have here of top P, where maybe we only want to consider the top % of the probability mass. Where right now, all 100% of our possible options are possible to be chosen from. But instead, maybe we want to restrict it to only be, let's only pick the things that constitute the top 70% of our probability here. So banana, 67 plus apple at 17, that adds up to be a little bit more than 70. So we'll only consider these for when we do our random sample. And this gunk at the bottom, maybe we'll remove between face, phone, and table. And these relate to each other in that if we're controlling our temperature, which is changing that probability associated with it, that it changes which things get included in our top P% of it. So when you're altering these, do them one at a time because they interact with each other. Basically, it's the takeaway, part of the takeaway there. But the other takeaway is that there are special knobs we can use to influence how creative and random our tokens actually are. So we do have some control over it. All right. Any immediate questions on these two, top P and temperature? Does this make sense? Kelsey, does this make sense? When does this make sense? Okay, let's move on. So here's this idea. Okay, so we can have some control over our probabilities associated with picking the next token. How much control could we have? Well, this is super powerful. We can use something called structured outputs to cleverly constrain the model to only output valid JSON according to a provided schema. So let's give an example. Let's say we have our object of a stoplight color that's backed by an enum that it can only be red, yellow, or green. And we give our model some input to signal drivers to stop. What color is the traffic light? And we have the start of our stoplight color object here, and we're asking it to predict this token. Well, based on what we know so far, the model will generate some scores associated with all the tokens it knows, and there's 20,000 other tokens underneath this. And we see that it'll probably, hopefully pick red, but it might start writing a sentence for us instead of like, oh, the signal color is that. Right now, there's a chance that it won't pick one of these things that we like. And what we can do is, instead of just letting the model sample from its probability distribution and assign its own scores, we can overwrite these scores before they get converted to probabilities and overwrite things that wouldn't be valid. So with code, we can look at it and say, oh, the phone token wouldn't fit here. It's not part of our enum. So let's set its score to 0 and make sure we can't choose that. And now we're able to filter our tokens to only ones that we say would be valid. And so now when AI generates from this, it still might pick a wrong answer of yellow here, but it will at least be constrained to the tokens that we think are valid at a time. So we can make it output JSON, it's constrained to a schema. And it's not just asking nicely, please give me this JSON schema back. We can actually force it to only be able to pick things that could be valid based on our schema.
And this is helpful specifically for devs because it guarantees that we can parse into and out of known objects.
But it's something you have to explicitly do. Every API will be a little different, but it's
Does
something.
this change the model, or does it just reject values that aren't those and then go back and get another one?
It changes the score. Like it changes the score that the model has done before it can sample the next thing. So it's the code hosting the model is actually changing the scores, which change the probability, which change, or it could just set the probability to 0, but then like here, let's say, anyway, it's actually changing it. And it's not just like repeated sampling, it does this before it then picks the answer. So it's calculated the scores, and then it's overwriting the scores.
Does this step occur before or after like the temperature check? Because say you have a really low temperature or like a really high top P, like say green and yellow aren't even options, like it's only red and the. Would you ever get, in that case, the ability to have yellow and green because of this override, because those are now valid options?
That's a great question.
Or just based on the output set?
Let's see. I didn't understand that very end there, but
So like, is it, if the output set that they have is only red and the, and then you say, hey, it can be these three things, are you then filtering on the union of the set or the intersection? Right, so are they gonna add yellow and green as like really low probability because?
Oh, it won't add more in.
Okay,
Yeah,
so
yeah. So
it goes
it's
off-
restrictive. Yeah, yeah. Restricted what it has. And pretend there's 20,000 other tokens under here where none of them have a probability of actually 0, but they're all very, very low of like 0.0001. And so if you were to like say schema filter it down to two things that are both 0.001, I don't know this. That's a great question. I have to assume that the temperature adjustment happens after that, after going from the score to the probability, but I don't know that for sure.
So then in that case, if you have only yellow and green, right, the even is maybe incorrect from our side or whatever, but yellow and green.
Yeah.
The before schema filter doesn't even have yellow or green. and
So
then
fourth
try to
schema
find-
filter will have yellow or green.
But if it doesn't, say just
It
in the
will.
case.
It will. It'll be a very small number potentially, or a big number, but it will
So
because
this happens before temperature and top P.
yeah, I think so. Yeah. Oh yes, I see why you're saying that. Yes, because top P does another filter, and that filter would be after this. Yes. I have to imagine that the filter is afterwards. I don't know how it would work otherwise, because then you could potentially have no valid tokens.
Yeah.
You would give up. Okay. Great questions. All right. Takeaway here: structured output's good. We can have very precise control over our next token generation beyond executing nicely. Let's keep going though. So some of the implications of this this flexible token input and the idea of scores, that every token that we're feeding into the model affects the math that's happening. That idea of attention tries to mitigate this, that if something doesn't seem relevant, maybe it'll get lowered down, that it'll have a lower weight in the calculations, but not 0. That those extra tokens, let's say I'm asking you that same thing. That monkey ate my, one example, and then let's say I ask Copilot in another window, I like Shakespeare, that monkey ate my, what is it going to calculate next? Well, if we go through the calculations that it's doing along the way, we would think that this wouldn't be relevant, but there's still these tokens and the vectors associated with it, their embeddings, are still participating in those multiplications, and it can have an effect on the internal scores that are being generated, which will affect that probability distribution, which will probably change what token gets selected. So if we look at our scores between these two examples, these are hypothetical made up, that in our very clean input that doesn't have that extra noise of I like Shakespeare, our banana has a very high score and book has a very low score. But by adding Shakespeare, our token has shifted its attention a little bit towards these literary concepts, that book is slightly higher, banana is slightly lower, that this stuff that doesn't feel relevant is still introducing noise. And while sure, maybe most of the time it'll pick banana here, we've decreased the likelihood that it'll pick banana, where banana is the token that we want it to. That adding noise affects this probability distribution, even if it seems like an innocuous, irrelevant detail. So you should be very careful about what input tokens you're feeding to a model, because it'll have some effect. And over very long input sequences, you can get some kind of attention drift where maybe the model will focus more on some of the recent tokens, maybe more on like the later tokens, that where your details are, it may focus on the wrong thing. And you should just be very careful anytime you're trying to put a very long input into a model.
And this really is the attention stuff, because it may wrongly give attention to a different set of words. Like it may pay a lot of attention to these other words that are kind of extraneous.
Definitely.
Especially, and this is especially true when you get words that have multiple meanings.
Mhm.
And it's like, oh, there's a meaning that actually of that word that actually ties to another set of words. That can really mess things up.
Yes, definitely. Very careful what you put in.
Like I was searching for a thing with AI this morning. There's a rack mount mixer that I'm waiting for. That is a particular, it's the name of the mixer, but then it goes in a rack. And so getting it to unattentionify or get the attention in the right spots for the right kinds of words was difficult. I could see it struggle.
There's an interesting case where Mark and I were in a meeting and Mark had asked, who's doing stuff with a customer, and it didn't pull like a certain thing of data. And we went in and we just updated like the description on that data point definition. And as soon as you update the description, it started pulling the data. And it was just telling AI a little bit more context and just be more specific in the prompt that you gave it. And it just did a better job. And I've seen this just with code too, like just having a change in your prompt slightly just changes it. So changes its results in such significant ways. It's impressive. Do you want me to grab that?
Okay, great stuff. see, we have 13 minutes left. See what we can do. Okay.
More questions.
No more questions. Great. All right. So far, we generated one next token, our banana or apple. What if we want a full sentence? Well, it's pretty simple. We can just rinse and repeat that process multiple times where as we're generating new tokens, we can just take that output token and append it on to our input and run it again. And just keep going. So banana, now banana participates as part of our input. That monkey ate my banana and it hurt my feelings. Very sad. So that's it. That's the simplest secret to getting onto the next token. That we just take the whole output that we have so far and feed that back in as part of our input. So the takeaway there is that you should think of every next token as like a stateless operation. That each token is generated based on all of those previous input tokens, and the model doesn't remember anything beyond like the current context of current tokens you're giving to it. It only sees those tokens you give it in the current generation, and each generation of a token is really taking that whole thing and plugging it back in. Now there's some intermediary calculations you can cache for performance reasons, but like fundamentally, this is really it. That you're really taking that whole output, feeding it back in. That's important. It's a very important implication of these autoregressive models. Autoregressive just meaning the next output depends on previous outputs, and we keep feeding the thing back in. That it has an implication for prompt design and how you ask it to answer questions. So imagine on a math test that you're asked to write your answer and then write your work that went to that answer. Is that different from instead being asked, write your work towards the answer and then write your answer afterwards? Do you think it is? What do you think, Wendy? Yes, series of calculations to get to your answer. So if you think about it from the LLM's perspective and what information it has available to it at each step when you're asking it to answer that, let's say we give it a prompt, you buy 4 candy bars for $2 each and pay with a $10 bill. How much change do you get? When it's generating that next token, if you ask it, like, just give me the answer, all that it has available to it for its processing is just that prompt, those tokens that came before it. Now instead, what if you ask it, you buy 4 candy bars, thing, explain step by step, and then return the answer. And we think about what calculations it's doing, what information it has available to it at each step along the way. That as we're feeding tokens back in, it first writes step 1, find the total cost, and it has this operation it has to do. It's pretty simple, 4 times 2. It can probably get that, but that's 8. And then the next step of calculate the change as it's building in. And we finally get to the point where it's having to give our answer to us. When it's generating that final output token of the answer at the bottom there, it can look at those previous output tokens that it's done along the way, that it can look at its work, so to speak. And you should, this is very important, that you should think of each token being generated as a subproblem. And you can solve those easier subproblems first and build onto it. That you should think of every token generated, every output token, as input to the model itself. And if you design your prompts in the right way, you can get the model to prompt itself to work slowly towards that right answer, as opposed to making that big jump to that right answer.
And one example would be when we built AIS, we would give it a meta prompt. It says, hey, I want pictures of people that look like Clayton Gravatt, right? And so it would come up with like just very, very limited depth and variety. But when we said, okay, now make 5 categories, and then for each category, make 5 subcategories. And now for each one of those, generate 2 different detailed prompts based on the meta, the category, and the subcategory. It had all kinds of detail that I can post a couple of those pictures that it did come up with. But,
I'm curious what I look like. What other categories do we have for Clayton? Yeah, it's a great example.
Yeah, just and having it go out and do steps. Like when KSAM, one of the things we're looking at is, okay, can you create the steps that would be required first, and then break out each step and do each step? Because when it just has a hard time doing many, especially somewhat unrelated things, without getting caught in itself, or if it gets too big, it starts to let go of the original context. And so keeping those windows relatively small.
Yes, so very important things to consider along the way. That the big takeaway from this slide is like the order matters for what it's outputting. And with like that category example, adding that category helps it then generate the next token that should be associated with that category. But having it build itself out that way and giving it direction on how to build itself out, where it has to find very different categories and what tokens should fit within those categories, is helpful, as opposed to just saying, all right, be very creative and try and come up with a very creative different set of 10 prompts. If instead you can guide it into like, okay, let's get a category, guide it into that, it can fill in for that category, generate another category, it can fill in for that category.
Question.
Yeah.
So that's for tokens. Like it could, I understand for tokens, it just kind of builds off of its previous token as an output, creates a token, builds off that. Is that also how context works? Like,
yeah, so context, I may have used it in a couple ways here, but a context window of the number of token, let's see, a context window is the number of tokens that a model input at a time. So if we go back to this step, how big you can make this sentence is, let's say, the context window that the model can pay attention to, or that the model can process while trying to get the next token. That every one of these tokens, like that, monkey, 8, mine, these are all used as part of the calculation for generating this next token. And models do have a limit on the number of these that you can feed in.
okay.
I think if you guys were at the company meeting, watched the KSAMP demo, a good real world example that's pretty simple is Elizabeth wrote some code to give a status to a case of like stable, needs attention or urgent. And we asked AI to first explain why it thinks it should have that status before it gave that status. So it's like asking it, figure out status, explain to me why you would give that status, and then give it the status. Instead of giving it the status and then explaining it, it's like the order of that changed how good it did.
Yep. Very good examples. Okay, we have 5 minutes. I'm gonna go a little over. I need to get to slide 22. This is very important. Okay, let's see. So do we just keep generating, right? Do we just keep feeding it back in? Well, we don't really want it to just keep generating tokens forever. Eventually we need it to return a response. So we could do this a fixed number of times, let's say 10 tokens, feeding it back in, but it's kind of hard to predict in advance exactly how many tokens we'll actually need. So instead of having a fixed amount or letting it go forever, we can introduce a special token, just as part of its vocabulary, just like any other word, that the model can output when it decides it's finished. Think of this like giving it a special period at the end of a sentence that it knows how to output, that the code running the model can recognize. So I've made up one, here it's called end of text, that we, here we are in C# again, that we have our input tokens, that monkey, 8, mine, and we just have a while loop that's calculating our context, that's our input tokens, plus any output tokens we've already generated. To start with, we don't have any output tokens. And we have some cool generate next token. That's all that math we saw on slide 13. And if that next token is this special end of text token, then we break out of our loop and we return this on to the user. Otherwise, we just keep adding that next token to our output tokens, and that builds up over time. So the takeaway here is that we can also teach our model some special tokens that the code running the model can interact with and look for. We might call these control tokens. And these are helpful for other things too, not just for output, also for how we can, let's say, structure a conversation. So if you remember that in order to generate the next token, we have to feed in the whole input so far, plus any outputs we've already had to keep building on top of it. If we wanted to have a conversation, we'll need to be able to feed that entire conversation back in. So we need to be able to feed in both what it said so far and what our user is saying, what we're typing to it. And if we could just stuff all those tokens into one very long sentence, but it might be a little bit hard for our model to figure out who's saying what. So instead, maybe we can introduce some other tokens that we can use to delimit our sections of our prompt. And we can even go so far as to maybe when we're training our model, maybe train it to pay a little more attention to our system prompt. Maybe these are some instructions we give it. You are a helpful assistant that responds in haikus. Maybe we want it to more often paying attention to that. And our user has put in, what's the weather today? This is broken into tokens, but around these tokens, we input our special control tokens that our model is able to use to help figure out, okay, where is this? What do these tokens mean? Oh, this is my user that's input this. And then maybe our assistant response comes back and it's written our nice haiku for us. And then if we wanted to get another sentence, maybe our user asks, what about tomorrow? We'd feed all that back in, plus another section for what our user has said here. So this is kind of showing two things, both a different type of control token and also part of the reasoning for why prompts are usually like arrays of chat messages between like our system prompt where we're describing how we want our model to respond for the rest, then our user, then our assistant, because we need to be able to feed all of that back in to have that conversation keep going. Okay, we've made it to slide 22. This is, in my opinion, one of the most powerful uses of these special tokens. Something called tools or function calling. I'll use them interchangeably. They allow us to do all kinds of cool things. We can use it to describe code that we want our model to be able to interact with. So let's imagine we have this C# method, get weather, and it takes an input string of location. And we want our model somehow to be able to interact with this. Well, we want our model to be able to interact with this to be able to respond to things that our user is asking it. Like our model doesn't know what the weather is today, but if we give it this function, then it can call code to figure out what that is. So let's go through what a flow might look like. So what we can do is we can have just another special section in our input prompt or input set of tokens for a definition of a tool. And we can define our C# method, our get weather method, just in JSON, and that JSON gets broken down into tokens. So we've told our model, told it, as part of our input tokens, we've told it about this function up here. And now we've also given it our user prompt. Our user is asking, what's the weather in Seattle? Now what our model does, it's very interesting, because it has these tool definitions and we've given it some other special tokens, we can let it emit function calls where it describes how it thinks we should call that code to help our user along the way. So it's emitted just tokens. Say the name of the function and the arguments it thinks we should put in that function. And we could even be clever and use our structured outputs here to make sure that when it starts generating this, it actually adheres to whatever schema we have for our location. And that's it. So we can monitor for these function calls. Let's say some example code here that's monitoring our tool output to see if it has a function call in it. I should probably have this as a function call end here. Let's not pay too much attention to the code. So if our model has output some tokens and those tokens contain a function call, we can extract out that function call. We have some helper method that parses out the name here, and we can parse out those arguments for it. And then we in our code just take that string basically that is given back that token, and we call that method. So we might have so if it's output a get weather token, we parse that out. We might have a big if ladder that says if call name equals get weather, then call get weather, and then we'll return those results back up. So very importantly, we have to return those results back up to the model for it to continue generating. So let's add in our function result to it, and let's see what our tokens look like now after it's emitted that function call, and we've given it a response that we can see our tool definition still. Again, we have to feed the whole thing back in. It needs all the tokens to know what comes next. We can see our user prompt. We can see function call that it's emitted, and then we've returned back up the response, our function result. Let's say that our C# code has written back that the weather in Seattle is 68 degrees Fahrenheit and partly cloudy, and now we've given all those tokens for the model to work with, and then we can get a final model output where it says, okay, based on the weather data, it's currently 68 degrees Fahrenheit and partly cloudy in Seattle. That this is the flow for how AI models can use tokens to interact with our code because we just parse that out. So this idea of function calling, along with structured outputs for making sure that those generated arguments actually match that function signature, is the key to building agents, these AI-enabled systems that can actually do things. And it's all powered just by these special tokens.
I think what's important is like this is enabling AI to call explicit deterministic code.
Or just code that can do things, both get more information or update the case status. Like this is how code can interact with that LLM. The LLM can help us do stuff with code. Okay, sorry, I know we're going a little bit over here. I'm good to keep going, but if anyone had 1 o'clock, now's the time to run.
I'll monitor the chat. I think we've lost our chat monitor.
Thank you. Okay, so very powerful. Tokens are awesome. There's a lot of these to keep track of. Do we need to know them all these tokens? The answer is luckily no. Most users, you don't actually need to handle these special tokens directly. When you're working with these cloud hosted
Oh,
models.
your screen share got dropped when you changed.
Thank you. Thank you. hopefully I've been sharing before that.
He just messaged that at 102, and if 102 right now.
Okay, thank you. That's funny. Okay, let's see, where are we? Okay, so we're doing something with our special tokens. Oh, we don't have to know what these special tokens are. So instead, luckily, OpenAI is hosting that model. We're interacting with OpenAI's API, and there's some nice SDKs built on top of it, but fundamentally, we can just interact with JSON messages, parse back and forth, that our messages array, rather than having to know what that special token is, we can just use like a chat request user message and a string, and we can build up our array of tools. And parsing responses, we don't have to know what these tokens are. They just look more like objects when we're interacting with these nice APIs for us. So it's a very nice level of abstraction. So fundamentally behind all this, it's just a bunch of tokens, but us as developers, we're just writing code. And when you're interacting just with those APIs, you still have to do things like parse out the function results, parse out what functions AI wants you to call as part of those tool calls. So you have to have like a little if ladder, if equals get weather, then call the get weather function. And you still have to write like the JSON schemas that are associated with these. If you want to use structured outputs or you want to describe how your tools require the inputs for it. So you still have to write the JSON and the if check to execute the C# code. Or do you? It's even simpler. So this is where semantic kernel comes in. Semantic kernel is a very helpful library that automates the construction of those JSON schemas and that function calling just with simple C# attributes. That I'll get through that top bit. But if we want to use structured outputs by constraining our model to something that looks like a valid JSON, we can actually just use a C# object defining our weather result here. And if we want to use tools, instead of having to have our if ladder to parse out the call, we can just decorate our function as a kernel function and maybe give it a description for what it does and how our AI might want to call it. And I'll scroll down a bit here. Let's not worry about too much about creating the kernel initially, but in order to allow that function calling to happen without us having to parse out the response and do if, then call this, you can just use a function choice behavior equals auto. And for defining our structured output result, instead of having to give it like a JSON schema, we can just do a type of weather result with our C# object. And then our result is just a kernel.invoke prompt async. What is the weather in Spokane today? Plus our settings. Semantic kernel nicely handles those JSON schema generation and if this call this function for us. And then we just have a result toString that we can deserialize into our weather result object. And now we're back to just having an object we can work with, so we can print out its weather.location or weather.temperature. So it's very nice. The takeaway there is just semantic kernel is awesome and it makes structured outputs and tool usage much easier. So putting it all together. So with all these quality of life abstractions, writing AI applications feels a lot like just programming again. But now that you understand a little bit about what's happening under the hood, hopefully you can write better prompts and design better, more effective structured outputs. So let's take a quiz. Let's see who's paying attention along the way. So which of these is better and why? Lucy, I think you just volunteered. So A and B, if we were using this as our structured output, which of these would be better if we were asking to solve a math question?
Oh, it's just flips.
Mhm.
I think reasoning always goes first, so I'll give option B.
Perfect. That is correct. I'll press this button just so it shows up. But yes, thank you. Okay, great. Yes. So ordering of your structured outputs matters. There's a bit of a jump there that the model will output things in the same order that you're defining your objects here. So putting the reasoning attribute before the answer attribute means that it will do the reasoning tokens before it does the answer tokens afterwards, and it'll probably get better results.
Do I have to ask it in prompt to do reasoning first? Like, what if I flipped my way in the prompt versus my structured output? Does that matter?
If you flip your way in your prompt, you are asking it nicely, please generate these first, but then your structured output is forcing it to not do that and will force it to do the reasoning ones first.
And
the one that matters is your structured output.
is there like attributes in semantic kernel so you don't just have to have reasoning then answer always, because that seems like very hand wavy. Oh, just make sure that your result object is at the bottom and all these other things, like what if one is in private method, what if one's in public, or whatever it is.
Yeah, semantic kernel will respect some like JSON attributes. Like if you want to give it a different name and like a JSON schema, you can do that. And I think it respects order too.
Okay.
But I don't verify
It's a
that.
straight JSON class. It doesn't really matter what
Yeah.
the origin is. Okay, that's cool.
Yeah, well, if you're passing this in directly, it very much matters. But if you have JSON attributes on top overriding
That's what I mean,
how
that's
it
what I
gets
mean.
converted into JSON,
Yeah.
only that JSON gets passed up to the model. Semantic kernel sees your C# class, and semantic kernel will generate that JSON schema for you, and it should respect most of the JSON schema attributes that you might be familiar with. Good question. But in cases where there's a bug in semantic kernel or it doesn't respect that one attribute, yes, you're stuck changing the order on your.
I guess Kevin's question to Sam's mind, like the declaration order is bad. Like that seems like a half-baked solution for like, you should be able to attribute, but if it's just based on system.text using JSON, that's easy enough.
Yeah, you can override it then.
Whatever we want.
Does the order matter for parameters in a private function?
Yeah.
It'll go from the first one.
Should, yes.
So if you pass reason into a function, you don't have.
You should probably pass reasoning first into a function.
Okay.
Yes, it should respect those orders. I double check by looking at, yeah, it should. You might want to intercept the arguments instead of doing an auto function call. Instead of setting it to auto, you can do it manually and have to parse it back yourself just to double check. But I'm pretty sure it would respect the order of the arguments, but I haven't actually double checked.
And it looks like Andrew Scott opened an issue on June 18th about not respecting JSON.
Okay, so there's some that it doesn't respect, yeah.
To be fair, I think like half of the AI stuff that we tend to use as devs is still like preview version.
Yeah.
So, I mean, opening issues seems like a very reasonable thing to do.
Semantic kernel is also open source. If anyone wants to fix that and has some extra time on their hands, go for it. All right, who's our volunteer for our next question? Why should you avoid adding extra irrelevant information to your prompts?
Shakespeare makes monkeys eat books.
Shakespeare makes monkeys eat books. I'm not even going to hit the reveal button because you nailed it better than I could write out an answer. Yes, just be careful about what you put in. Okay, what's the difference between using structured outputs and just asking nicely in your prompt? And to give an example of asking nicely, please give me a JSON that has this attribute and then this attribute versus using structured outputs.
And then constrain the model to do it. The other is a suggestion for the model to do it.
Yes, one is,
It's deterministically going to happen.
yes, great answer. One, you hope it's good. If you just ask nicely, you can hope it'll do it, but it won't always. And necessarily there's a randomness baked in, so it won't always. But if you use structured outputs, you can force it to always, unless you ask it to like build a bomb or something, then it might reject your request. But otherwise, you don't have to worry about JSON deserialization errors. There's some other things that can happen. Yes, great answer. All right, last question. Why do language models struggle with math and counting letters? What's one reason? Kelsey. Tokens. Yes, exactly. This tokenized representation makes it very hard to represent big numbers nicely. Very good. Awesome. Well, thanks everyone. That's the end of my slides. Any okay. Any questions? Any other questions? Any complaints?
Well, the question about the robot wars, but
Well,
who's gonna be the first to go? And it's
yeah.
Did you make this presentation with Claude?
Yes.
Nice.
Well, partially Gemini, partially Claude.
and partially you.
And a little bit, actually, it was a lot me. So so the way I made this was, you'll notice this is an index.html sitting on my.
Yeah, it's high.
Yeah. So I actually wrote. This was an interesting.
Send me the link, I'll go to it.
What's that?
Send me the link, I'll.
Oh yeah. If anyone else wants to see localhost.
Paste it in the chat.
No, I won't do that. I could publish it up somewhere, but I don't think it's that useful. It was interesting. As I was thinking about how I was going to make this, I thought, oh, I'll make a PowerPoint, and I thought, well, I want this interactive thing in the middle. It's like, well, I don't really know how to do that in PowerPoint. I can make like an animated GIF and put it in, but you know, I might as well just like, if I'm gonna make a graph thing, I'll just make a graph thing in JavaScript. And I could just actually build the whole thing in HTML and JavaScript and CSS. So I wrote all these slides in Markdown. And when like graphs go here, and then I handed it to agent mode, GitHub Copilot agent mode with Claude Sonnet 4, I think, and it got, say, 90% there. I was really impressed. And then I had to like, you know, the last 10% was a lot bigger than the
Yeah.
a lot bigger than you want it to be. But it like surprisingly well, and then a bunch of little tweaks. Like the at first the lines weren't actually on the graph. They were like kind of off to the right. So like put the lines actually on the graph, and then it did it. So I was very impressed. But it's just like an interesting commentary on which tools you use to make things, because AI is so good at writing code. Instead of doing this in PowerPoint where I have to manually press the button, instead I can give it to AI to write code, which seems like it should be harder, but it's actually faster because AI is so good at doing that and not at pressing the buttons in PowerPoint. A little weird. All right, what else?
And to clarify, AI is only good at writing code if you are good at asking it smart ways to write the code instead of just saying the one thing. Like I feel like when I see AI write code poorly, it's often because it was like asked very poorly or something. And then when I see it writing it well, it's usually because I've asked it something that's pretty specific, and that's like, I don't know, I've given it like the right context.
It's a very box thing that you
Yeah.
can do. It's a function of the author.
It's just really
You're just.
You're just bad at the prompt engineering, guys.
Yeah, I go with the brute force asking things. No, actually put the link on the graph, and now we'll put the dot on the graph too.
To be fair, I did not ask it to put the line on the graph to start with.
No, that's
Easier.
better.
You just
Yeah.
gotta tell it exactly what you want, and then it will do it.
Thinking with like in response to the API and stuff, now that you can basically it'll store context for you. I noticed that when you use MCP calls, it still expects you to send it the last, even if you give it the chat ID that you're on, the thread ID. It's still, when you do MCP call, it still expects you to add the function call to your MCP response before you send up, which seems weird because it has a context thread. Why does it need both in that case and everything else in your cover?
I don't know. You'd think it would keep track. Yeah.
Just seems like a weird thing.
Yeah.
Why-
Well, let's see.
You're right, you wouldn't need that.
Yeah, because if it has it, it shouldn't need it, but like it needs, let's see, ultimately when it tries to generate that next token, it needs both the function call and the function result to it. I don't know why they wouldn't be able to keep track of those.
Yeah, I do know.
But
This is the one thing I haven't figured out when doing that is you have to, well, first I kept just giving the function results and then the chat thread ID, and I can go, hey, what are we talking about? I can know the entire conversation history, like
Yeah.
exactly. But then I'd go, here's the result, and it goes, it'd give like like some HTTP error where it's like, I don't know where the function call is. Or if you do a function call and a result, and then you ask it something else after that conversation, they'll then go, your tools level just like, your tool's gone. And I'm like, do I, like, I haven't yet figured out the relationship between like the thread that knows what thread you're on, and like you have to still manage, like state manage.
Yeah.
Functions.
I think the takeaway there is OpenAI has a very small underfunded company, and with $5 billion more, they could fix that for you. But otherwise, use the chat completions API. All right, I will stop the recording here. We don't have to stop. Fun goes on, but I don't actually noticed.
Go to more recording and transcripts out.
Awesome.
Thank you.
Thank you.